Hello, we will be discussing today stereochemistry, 3D stereo, the structure and function of molecules. We can discuss chirality, asymmetric carbon, and CIP, Kahn-Ingold pre-log rules, and the Fischer projections, how to use it to determine absolute configuration. Okay, now, so let's get started with an achiral or achiral molecule. So this is a symmetric molecule. So that is methyl and methyl groups attached to the center carbon. And there's hydrogen and there's a hydrogen here. Now this one is sp3 109 bond angle tetrahedral species. Now we can compare that with the different one. So versus chiral molecule. So a chiral has a asymmetric center, or we call the asymmetric carbon. So let's put carbon, center carbon, methyl, and four different groups, something like Br and Cl and hydrogen. Right now, this has four different groups. sp3, that's the most important thing. It's a tetrahedral carbon, right? And the four groups we call the tetris, so it's four different ones. So that center carbon is called the asymmetric carbon, or we call the asymmetric center. Okay. Now, so why we are talking about that? See, the achiral ones are like socks and letter A, letter B. They have symmetry. Look at your shoes. You cannot switch the left and right. The letter Q, letter R, they don't have symmetry. Your shoes don't have symmetry. That's why you can't switch around, right? So that's very important. You will not be walking properly if you switch your shoes, right? Let's see the difference. So let's draw a mirror for this molecule. Exactly draw the mirror image. Okay. So hydrogen closer to the mirror and the chlorine closer to the mirror, methyl up and Br to the away from the mirror, right? So we copied that one. Now, one is object, one is image. It could be switched around, doesn't matter. So one object, one image, either way, right? Now, what we can do, we can use the Kahn-Ingold prelog rules to find out the absolute configuration. So the CIP rules are, it's easy. So the rank the each group based on their atomic number. Higher number gets one and hydrogen gets the last basically. So 1, 2, 3, bromine heavy, highest atomic, chlorine, then carbon, then hydrogen. Then hold the last one, last priority one, the number for hydrogen away from you, and they take the rotation 1, 2, 3 order. So 1 to the 2 to the 3. So this looks clockwise. It exactly like clock turning their arms around it, right? So that's called the R, the right turn, or the R. It's also rectus, and it's count clockwise, right? Now the other one, the mirror other side should be S, simple, right? That should be counterclockwise. But we're going to look at it whether it's true. So look at priority 1, 2, 3, take rotation 1, 2, 3 because hydrogen is back of the screen, so it's counterclockwise. It's turning left. That's called the S or sinister. Those are the absolute configurations. Practice with my few questions that I will do later. Now this one is a simple concept to understand very easily to understand what's chirality. This is called the polarimeter, and light passes through the polarizer. It makes plane polarized light and it passes through the sample and then it gives you a degree reading. Plus 12, plus minus 12, whatever the reading you get from the detector side. Now, if you have pure S compound, put it into the polarimeter. Let's say you will read 14 degrees. If you put the pure R compound, you should be reading negative 14, right? And that is called the optical activity. So there's no relationship between R and S and the optical reading. These are experimental and theoretical, two different things. Now, if you have one-to-one mixture, that's called the racemic. Why the racemic is zero optical rotation, zero optical activity. Why? This 14 plus cancels 14 minus, right? Half of the sample cancels the half of the sample's activity. Now, this comes a good, not good, but it's really a terrible example. Thalidomide. So perhaps you should read about thalidomide babies and what's the R and S um, compounds did to 10,000 babies who were born without arms and legs, basically in the 1940s, because the one of the molecule worked as a drug, the other molecule worked as a teratogen, right? It's actually interconverted within the body, but go to your MMI with the knowledge of those. Okay, so let's look at this one here. Yes. So we talked about the absolute configuration, racemic mixtures, and polarimeter readings, right? Yes, that's good. We'll look at the Fischer then, right? Okay. So the Fischer projections are an easy way. Uh, Dr. Emil Fischer came up with the idea to draw sugars and show them in an easy way. The idea is like something like this. See, the man is sleeping happily. You wake up the man, throw him against the wall, and he's pretty disappointed in a way. But it's a simple way to look at the man's height and all the details. That's kind of the idea in a way, right? Now, the zigzag form of the carbon, actual 3D structure of these carbons can be drawn this way. So it's a tetrose, but I simplified with a methyl group. So this tetrose has 4 carbons, the head group, the functional group on the top, and there is 3 more carbons, methyl the tail in the bottom, and the center 2 carbons are like bow ties coming to your way when it is drawn in a Fischer projection. Or we call the Dr. Fischer gonna hug you, right? Kind of like that. Now take the R and S configuration for each chiral centers. The first chiral center is the second carbon. Let's get there. Yes, that's 1, 2, 3. It's R, and the other one is looks S, but it's an R because the hydrogen is in the front. Okay. Now um, we can. So that's the real 3D structure going into the Fischer. The Fischer is in your right side with the kind of the bow tie style, and you can also go in between the screen and the wall, and you can look at from your right side or left side in order to draw that, right? I'll get more examples to draw this, but I want to get the idea here first. Now, so if I have this Fischer structure, I can simplify. The vertical lines are going into the screen or into the page, and horizontal lines and atoms are coming your way. Now I can show it exactly. R and S, the second carbon R configuration, third carbon S configuration, right? And so that's what we know. Now let's draw the mirror image. It's easy. Just switch them, right? Draw a mirror, draw the same molecule as you can see it in a mirror, the image. It should theoretically show R to the S, S to the R. That's called the enantiomer pair. So this enantiomer pair, like I said, one could be a drug, one could be a poison, teratogen, right? Could be no harm either, but anyway, it's important, right? Now, if I switch one of the chiral centers, 2 bonds broken and fixed, it would be changing um, the absolute configuration. So let's say R and R went to R, and actually R and R went to R and S, right? So now R and S went to R and R, and then the mirror should be swapped, right? Now in this case, what you can see is, let's simplify, rather than the molecule, let's say 2 chiral centers, asymmetric centers, S to the R, the mirror should be, let's get a much simpler way. Yes, R to the R mirror is S to the S, right? And then let's say we break some bonds, 2 bonds actually, and switch one center to a S, and that's mirror would be S to the R. So these 2 pairs are enantiomer pairs. right? They can be formed only by breaking one center and two bonds, and then you will get it. But look at the red lines. Red lines are diagonal, and those are called the diastereomers. So the diastereomers are not mirror images. Enantiomers are mirror images. The diastereomers are not mirror images, right? And diagonal for diastereomer, kind of. And there's many more diastereomers than the enantiomers. You can see that how the number, right? So if you need what you want to do, you can put A, B, C, D onto each molecule, and you can actually group them. How many enantiomers? And there's only two pairs of enantiomers, right? So we already saw that it's A to the B and C to the D are enantiomer pairs. Everything else is actually diastereomer pairs or diastereomers, right? There are a lot of diastereomers here. Look at the red line, right? Okay, so we will do some practices later. So I just want to get the idea of diastereomers are more, and they are not mirror images of each other. And diastereomers are produced by only changing one chiral center. So those are the things to know. Good. We will look at how many we got. Yes, I think we should look at how many chiral molecules that we can produce, and that would be 2 to the n. So the sun has two chiral centers. 2 to the 2 is 4. We saw already 4, right? That's how we know it. Look at this one, cholesterol molecule. So the cholesterol molecule, it's actually part of steroids, sterols, and also vitamin D, and it's coming from the folic acid and going forward, and this is like very common. And this skeleton is we call the gonins or the sterols. A skeleton is very common in many important sex hormones and cholesterol. So this is actually the cholesterol molecule. If I draw these chiral centers correct, and let's put a double bond here, OH group here, and that's why it's cholesterol, right? And let's count chiral centers, how many, right? You can imagine how diverse the, so, oh, the other important thing actually, the cholesterol control is done by HMG-CoA reductase competitive regulation by using taking statins like Lipitor and other drugs, right? They actually control the HMG-CoA by competitive inhibitor, and that's how we regulate cholesterol level, right? So this one has 1, 2, 3, 4, 5, 6, 7, 8, 4 and 4, 8 asymmetric centers. So 2 to the n, 2 to the 8, that should have 256. So you can imagine 256 different stereoisomers. So you can draw it RRR and then 1s, and then you can change, but permutation will take forever, but we don't need to, right? And biological systems do have enzymes. We are not making tons of those, right? And so that's from the previous lesson, but it's the same lesson. I'm just trying to dub a little bit slower than usual. Okay, so yes, so importance of chiral centers and how many is the essence. Thank you.